Good evening. Welcome to this evening's webinar, Coding and Drawing with TI-Nspire CX II, if you have updated to that software and the corresponding handheld. Our presenter this evening is Peter Fox from Texas Instruments. Good evening, Peter. We do have him in the background there. He's muted at the moment, but we'll get him.
I'm out of mute now. Thanks, Brian.
Yeah, I'm pleased to hear that. Yeah, very good. Thanks, Peter. Now, I understand you're also doing something on the CX2 at the MAV conference. Am I right?
You are correct indeed. A bit beyond programming, we will cover some programming, but we'll go through some of the new features of the CX2, particularly the CX2 CAS, where you can, for whatever reason, disable CAS.
Okay. Yep. So that can be for jurisdictions that need to have that disabled for exams, I would imagine.
Correct.
Yep. So there's no longer then the need to have a separate handheld calculator for that.
That's right. Now, if they disable the CAS, you can do it just as a document and disable it. But of course, a student could switch it back on. So for assessment purposes, the requirement for a CX2 CAS would be that you would put it in press to test and disable the CAS functionality. Yeah.
Terrific. Okay. Well, it's all interesting and new things coming down the line. So I'm very keen to see what you've got for us this evening, particularly with the drawing commands. Now, viewers and listeners, I expect you. Well, I'm hoping you will have seen some of Peter's expert work before, either face-to-face at conferences or in earlier webinars that we've done. I've just been doing some research for my own MAV sessions this year, and I've actually been hooking into some of Peter's previous work on problems worth exploring and problems worth coding. And I've also seen Peter do those sessions live at various conferences. You can see on the screen his background, of course, is mathematics teaching in high schools, which he did for a couple of decades. While he was teaching, was very passionate about the use of CAS technology to the point that he's now working full-time with Texas Instruments and developing bigger and better things. So good to have you with us, Peter. We'll cross to you shortly.
All right, so let's get started.
Yep, all good here.
The first thing people will notice when they go into the programming menu on the CX2, and this is true for obviously the CAS and non-CAS, we're not using any of the CAS features in this thing, it's all just programming, is that this option to draw shapes, which includes lines, circles, rectangles and the like, polygons. It might not sound all that exciting, but there's some really cool options in there. Our first one is going to look at just the draw line tool. And some people might think, well, that's not all that exciting. I could draw one on a graph application, or I could do one in geometry. But there's so much you can do once you start drawing lines. For the, let's say, more elderly amongst our viewers, if you remember the funny little string screensavers back on, I'm going to say Windows 3.1, where you had this array of lines going and changing colours, you can do that. In fact, that's what one of the trainers in the US did with it very early on in the piece. We're going to do something different. We're going to do something which has a lot of mathematics behind it. So just to show that we can code, and as Brian said, I love the idea of coding for mathematics, not just, I don't count. Let's write a program to find out the area of a circle. That's why we have formulas. I want to code to do stuff. So the first thing we need to know is when we're drawing, it puts everything on a canvas. So it's not an application. It is what we call a canvas that will disappear once we get out of the program run. So once you're done with it, the canvas will go away. So that's the first thing we need to know. We're probably interested in the size of the canvas, so it's to do with the pixels on the screen, and also to note that 0, 0 is orientated in the top left-hand corner, and positive X moving off to the right and positive Y moving downwards. 318 units we can have to the right and 212 units to the bottom, which will make a little bit of sense shortly. And the other thing we need to note is when the program says finished, as it says on the screen at the moment, you just press escape to return back to whatever application you launched the program from. It may seem a little bit weird that the canvas just stays there, but it's actually very convenient because you don't want to just go pop and disappear, because you might be interested in the outcome, as you will when we progress through this webinar. And the other thing is that when that canvas is displaying, you can't run anything else. Some of us have used programs in the past that might be launched from a notes application, and it might be just sitting in the background resetting sliders or doing something. Once you do the canvas, you're on the canvas and you have to get off, in other words, out of the program to do anything else. So just be aware of that if you're drawing stuff using these new drawing commands. So I said we'd do the draw line. The syntax is actually pretty obvious. You can pick the syntax for all of these commands up in the catalogue, the little book. So it's pretty obvious. We go from x1, y1 to x2, y2. No brackets required, just commas separating our variables. The coordinates, of course, could be results of calculation, whether they be random or otherwise, attached to functions, whatever you like. But remember, we start with 0, 0 in the top left-hand corner. So if you think your drawings are upside down, back to front, or whatever else, then that's why. You can, however, change the window settings. So you can actually change how the canvas is sitting on the screen. So let's do some maths. Or for those of us north of the equator, let's do some math. So we're going to draw some lines on here on what we could call clock arithmetic, or even modular arithmetic. So I'm going to look at an interesting way to represent the 2 times tables. So 1 times 2 is 2, so I'm going to connect 1 to 2. And if anyone's seen Burkhard Polster's drawing on this, not his drawing, his YouTube video, that's where I got the idea from. And I thought, we can do this with Nspire. This is so cool. So 1 times 2 is 2, nothing exciting yet. So we've mapped 1 to 2. 2 times 2 is 4. We're doing a lesson in our 2 times table so far. 3 times 2, so 3 maps to 6. And 3 maps to 6, 4 maps to 8. And 5 maps to 10. And then 6 will map to 12. And we think, well, what are we going to do when we get to 7? Well, if I do 7 times 2, 7 2s are 14. We don't have a 14 on the clock. However, it's 2 minutes, or 2 units rather, past 12. It's a bit like 24-hour time. So 7 maps back to 2. 12 plus 2, 14. So I think we get the general idea. So 8 2s are 16. That's 4 past 12, or 4 and 12. So 8 maps back to 4. It's looking kind of symmetrical, isn't it? 9 2s are 18, just in case you weren't sure of that. And that puts us to 6. That's why I've got them in the little brackets. 10 maps to 8. 11 maps back to 10. And 12 will map to itself. That's a really interesting diagram. Doesn't look all that cool just yet, and certainly not particularly mathematical. What we're able to do, though, is explore what would happen if we used different times tables, or if we had more numbers on the clock. What if we had 360 numbers on the clock? What would the mappings and where would the lines go? So we want to be able to do that quickly and easily on the calculator using our draw line tool. So let's see how that would work. If we imagine it as sitting on a Cartesian plane, so I'm going to throw the Cartesian plane right in the middle, we should start thinking, looks kind of a bit like a unit circle perhaps. So therefore, if I said that that's 30 degrees for 1, we could write our x1 coordinates as sine 30 and our y1 coordinate as cos 30. I could have done them as 60 degrees, cos 60 and sine 60 and so on, but I want it to go around in a clockwise direction. So if you're thinking parametric equations, another thing you can check out now is the plot tool, the progressive plot for parametric equations. It's kind of cool in the CX2. And our next coordinate, x2, y2, would then simply be 2 lots of 30 for sine and 2 lots of 30 for cos, the 2 being our modular arithmetic things that we're doing before. And a tip here, by the way, once you start using x1 and y1 as variables, make sure you specify them as local variables. I got a bit tripped up because I went to do a parametric equation afterwards and it said you can't use them. And I thought, why? Well, because I defined them in my program. Remember, x1 is for our parametric equation. So make sure you assign them as local variables if you want to use those parametric equations, x1 and y1. It doesn't matter if you use x3, but just so you don't get confused. All right, so now we want to map 2 to 4. Sorry, yes, Brian?
I was just going to say, so local variables means that they are defined only within the bounds of your program.
Yes, thank you. Yes, just in case people didn't realise, good point. So local means that once the program is finished with, as Brian mentioned, you can use them any way you like, such as our parametric equations. So our next one, we want to map 2 to 4. So that position would be at sine 60, cos 60. And then, of course, when it maps to 4, we can just double our angle. So we can see our variables are going to be these 30, 60, 90, and so on. And the 2 times whatever our angle is will be constant for our 2 times tables. If we want to do the 3 times tables and have a look what that mapping looks like, we would change that part of our program to a 3, as we will do. Alrighty, so far it looks pretty easy. I could just draw lines and do that, but I think most people would realise those values are not particularly big. They're all going to be sitting on a unit circle, obviously, and our drawing canvas is a bit bigger than the unit circle, and it would kind of shove it up in the top left-hand corner, would have some negative values, and everything would end badly. So our unit circle centered at 0, 0. We're going to do some relatively straightforward maths, and we'll dilate it by a factor of 100. Then we need to translate our coordinates to the middle of our screen, thereabouts. So I figured if we translate them to 159 and 106, that should work. So let's have a look. We're ready to start our program. There's our defining x1, y1, etc. as local variables so that we can use them elsewhere once the program's finished. I'm going to set some values. hx is 159. You could just type these in. I've just set them as variables here. I could probably and should probably put them as local, but this means I could make this diagram bigger or smaller by changing the dilation factor if I'm not happy with my final drawing. It just makes it easy. It's all in one spot. And here's our loop starting up. So a lot of people don't realise you can put the step size in on a loop. So I've got from I equals 30, then it will step by 30 to go to 60, and then 90, 120, and so on as it steps around our clock. And our y2 coordinates would therefore just put the 2 in there. And you can see I've got the dilation factor sitting on sine, so it's even doing some mathematics here, just doing dilations of the functions. And then I just need to draw the line, and that's our program. Then we can mess around with the 2, we can mess around with the step size, and see what sort of pictures are created when we do this. So let's see how much of all of that I can remember on my calculator. Alrighty, so I'm going to start a new program. Control I, program editor, new, and I'm going to call this program numbers. And the first bit, and I'm just going to type this off the keyboard because it's quick, x1, y1, x2, y2. And we said that hx was going to equal 159, and what do I call it, ky, I think, for a translation in the y direction. And then my dilation was 100, and then I was ready to start my loop. 30 to 360 in steps of 30. All right. So far, everything is just typed in. I haven't actually pressed on the menu key to show you this little draw option down here. And we're going to use this draw shapes idea where the draw line is. And you can see some of the other objects like draw text, draw an arc, fill an arc, draw a polygon, and so on. We're not using them just yet. We need to do our X1 and Y1 coordinates. So let's do those. X1 is going to be assigned equal to our dilation times sine I plus hx. Y1 will be our dilation times cos I plus ky. Got that right. X2 will be assigned equal to our dilation sine 2I plus hx. And Y2, dilation cos 2I plus ky. Draw line. I could have got that from menu. I should, because it's in a menu and you'll need to know where it is. Menu, draw, shapes, draw line, X1, Y1, X2, Y2, and just in case you were wondering, in the catalogue, I go to draw, draw, it's a long way down, our catalogue's getting really big, isn't it? There it is, draw arc, draw circle, draw line, simple syntax, right? And that's the end of our loop, N4, and we're done. Now, there are some other commands. There's another one called buffer, so use buffer. I'll talk about that when we have a look at another project where we draw a chessboard. Basically, the buffer means that you can have all this drawing going on in the background and then paint it to the screen so you're not seeing it build progressively. In this particular example, it looks kind of cool watching the drawing take place. To do this one, I should probably put a wait command in, but let's just run it as it is. So Control R, which was another recent thing where you save the program and launch the program at the same time. So I'll press Enter. But well, aside from our drawing being upside down from what it was before, not particularly exciting yet. Press Escape and it comes back to where we launched the program. Another little command from our drawing menu. Menu, draw, control, and I can set the color. Notice the spelling color, and not surprisingly, those people that are familiar with Innovator perhaps will know this RGB setup and will therefore know that our picture is going to be blue. Let's try it. Now it's even more exciting. Yeah. But I did say we could increase the number of values on our clock. So I've changed the starting point from 5 and I'm going in 5-degree elements instead of 30 degrees. So we've got a lot of elements on our clock now. It's too late in the evening to work out what that is exactly in my head. But let's run that one. Now that's pretty. That's cool. Was that a round of applause I hear? Nice. All right.
Just the hearts, just people's hearts beating, Peter.
Oh, nice. Oh, was that like a cardioid joke?
Fair enough. Yep.
Dear. Dear. Yes, and we change the colour. Let's do a different colour. And of course, if I put a wait command in between each but I think even on the webinar, you can see that it's sort of progressively drawing that. It is very quick, and it's very quick on the calculator too. So don't be too frightened about, it's just going to take forever. No, it's remarkably quick. All right, so that was doing it that way. Let's change this value down here. So what that means, instead of multiplying by 2 each time, we're multiplying by 3. So our modular arithmetic has changed, and we'll see what sort of a picture we get out of that. probably should have chosen a different colour. That one looks a little weird, but never mind. But yeah, that's pretty cool. Some people might recognise these as something called epicycloids. Weird and wonderful names. So we can change them. You could, if you wanted to, put those as parameters in here and dial them up instead of coming back to the program. You could put another loop on the outside of that and just have it scrolling through all of these epicycloids, starting with 1 to whatever number you like. But in that case, I'd probably paint the canvas. So in other words, you use this buffer, which we'll have a look at later on, so that you can see one cycloid, then another, then another, then another. So what about some mathematics surrounding that? Let's change the colour back to something that's going to be a bit easier to see. I think the blue was quite good. That one. And the one I wanted to do was our one with the 2s, so our modular arithmetic with the 2s. Now, at this stage, you can't just copy from the canvas. It would be nice if the calculator said, oh, I'll save that as an image and pop it in a graph for you. It's something we can wait for. So with the power of computers, I'm just going to use the snipping tool, which you probably won't see on the webinar, but I'm going to just copy, and it's very rough. You'll see like a black canvas go over it, and I'm just saving it off to my computer. And we're back. So what I want to do is paste that picture. I'm going to insert graph, and we'll insert an image. Ta-da! So that's not exactly taken directly from the canvas. I used a Windows snipping tool to do it. So the question is, what would that equation look like? Well, fortunately for me, I declared my variables as local. So I can use x1. Had I not, if I type something in here, it wouldn't let me do it. It would say they're already used, they're reserved, defined, or something. So I'm going to take a stab in the dark. Not too dark. I've got a rough idea here. And let's go for 4 cos t plus 2 cos 2t. That kind of looks pretty cool, except for, Brian, you should have reminded me. Look at this. My calculator's in degrees.
You're in degrees there, Peter, so you'll need to do a conversion across there.
Thank you, Brian.
That'll do.
Better never than late. Sorry.
I was actually typing in a reminder to everyone about that local variable thing.
Oh,
yeah.
Okay. I'll take that one then. We can
yeah.
see that our
but
little
I would recommend a colour change here, though, because we've got blue on blue. You've got your graph.
Yep. That's a bit better.
That looks better. Yep. Upside down, though.
It is. So we can fix that. We can just reflect that a little bit here. We'll reflect upon those changes. But,
change. Very good.
And let's, there we go. That's a bit better. So there's our equation. Kind of cool. Now, the students may not have seen that sort of stuff before. There's some theme park rides that use that sort of an idea. If you want to present it more of the epicycloid sort of an environment, as we've got here, this is the circle rolling around the outside of another circle, and the cusps and the curves that we get. I've made this so that we can change it around a little. And if the outside circle is the same as the inside circle, then we get that lovely cardioid graph that we had before. We can drop the radius down a bit, and we've even make it round the inside if we like. Probably not sensible to make it the same size. This one's kind of weird. If you drag this one around, which is exactly half the size of the outside circle, the point traces a straight line, perhaps a little bit unexpected. Oops. So we get these weird sort of shapes you can get from it. Let's see if we can see the lines that go. Oops, the lines that go along with it. Yeah. There's our straight line. Oops, wrong way. Let's try this. There we go. Let's make it a bit bigger. So there's the sort of shapes we could have if they're on the inside. The one we did with our clock arithmetic was on the outside. And here. So there's a lot of mathematics you can do with that. One other one, which I'll show people. Let me just insert a geometry application, and I'll use my same old sad and tired joke. That's what the tree said to the bush. Gee, I'm a tree.
Hey, I'm a tree. Yes, okay. I got it.
Yeah. Okay. I won't do that again. I probably will, but not in this webinar. So if I put a point out here, and then I'm going to draw a line and bounce it off somewhere else. Now we're going to reflect that, so I'll need a tangent. That's a line. Just draw a line, tangent over here. I'm just trying to show people that there's so much mathematics you can do just from that one quick and simple little program. So next thing I want is, if I'm doing a reflection, I probably need to have a normal and transformation, do a reflection. There's my mirror, there's my line. So as this point moves, find that one, as this swings around here, what sort of line does that create? Or locus, rather. Oh, look, there it is again. They seem to be everywhere, these little cycloids, don't they? There's another cardioid. And in fact, it's the reflections of light as they fall into a cup. Next time you're having a cup of coffee, see if you can see the cardioid sitting inside. All right. I'm looking at the time thinking we need to get on to drawing some other stuff, but hopefully you can see there was a lot of mathematics sitting around just one use of the draw line tool. And I think, if nothing else, you could create lots of those pretty graphs and put them up on the wall and have students asking about them. I think that'd be kind of cool, but then I'm a maths nerd, so...
Yeah, we know that, Peter. One comment came in there was some people remembering the old spirograph. I remember having that as a kid,
that's exactly right. So I'm going to be looking forward to everybody's programs of spirographs, absolutely, which you could do using that same idea. You're absolutely right, spirographs. Beautiful, love them.
And of course, all right, string art, which I think you may have mentioned on the old nail boards.
Yep, and we've done some webinars on those, and there's some lovely activities on string art. All right, this one here is based on an activity. It's called pebbling the chessboard, and I've written this up. I've called it game, but we'll discuss what that means in just a moment. You'll see that it's launched my canvas. Up on the top of the screen it says running. It's not going anywhere, it's running the program, obviously. And the problem for people to solve is, you can see I've got 3 red discs. We'll call them filled circles in programming world. And I've got a checkerboard, which we'll call filled rectangles in programming world. And I have also used, which is kind of cool, the get key command, which I'll demonstrate in a moment, to listen to whether or not I've pressed the left arrow, right arrow key. So if I just click on the arrow keys rather than clicking on my computer, you can see that it's drawing a new rectangle just in here in light grey. Each time I click, it moves to the new location. Now, pebbling the chessboard says, all I want to do is get those 3 red discs out of that grey region. well, you could just pick them up and throw them out. But there's a rule, and that is, if you select it and press enter, it splits into two, one going to the right, one going up. Fairly easy. I've got one of those discs out already. Now, the problem is, if I wanted to get, say, this disc out the way, I'm not allowed to because another disc is already sitting in the adjacent square. So I need to get rid of it. I'll arrow over to that one, press enter, and now I've made some room to get this one out. So I'll click on that one and press enter. I've got two of those discs out. Looks fairly reasonable that I could get all of those discs out with only a few more moves, given that I've only had a couple of moves, and you could get the program to track how many moves so far. So I'll go back here, I'll press enter on that one. Now notice I clicked there and nothing happened. I have to press enter. I'll explain why in a minute. And now I'm kind of stuck because I've got a whole lot of circles or discs in the way. So let's make some room. Press enter here, and go up here and get that one out the way, get that one out the way, get that one out the way, and I'd love to get that one out the way, but there's a disc in the way just above it. So I need to move that disc, but there's discs either side, and that disc, and that, oh. So I'll move that one, and let's try and move that one, and we'll move that one out the way. So I can move that one out the way, and then I'm stuck again. Look, I can't move that one, and can't move that one, which means I can't move that one, which means I can't move that one. Now, spoiler alert, you can't solve it. It's impossible. Even if I made infinitely many squares on this board, which is not possible, but imagine we could, it's still not possible. The problem is impossible to solve, and that's one on our website, an activity on our website, and students try and solve it, and it's a lovely geometric sequence problem. You can solve prove that you can't solve the problem using geometric sequences, not just by exhaustion, but a proof that you cannot solve it. That was one that was done by the wonderful people at Numberphile, peddling the chessboard. So I wrote it up as an activity, and I used this programming stuff to get there. So, now you'll notice it still says running. I'll press escape. There's a finished. Press escape again. It returns me back to there. And for those that are wondering, how did I do some of the stuff on there, let me just show you D with some matrix. And you can probably figure out what each element in that matrix is representing. 0 means, obviously, that there's nothing on that square. 1 means that there is something. So basically, I record the current cursor position, and if it's on a 1, it says, okay, you're in a valid space to move a disk. Now check the row and column adjacent to you to see if they're empty, and if they are, then you're allowed to split and put 1s in those. Otherwise, it doesn't do anything and just goes back into the loop. So that's the guts of how the program is working, but we need to see how do we do the whole drawing stuff. So let's go back to here and have a look. Oh, we did the epicycloids. We changed some colours. I want a clear command too. I forgot to mention the clear. You can clear the canvas. So in other words, scrub everything off. All right, so draw rectangle. That's another command in our drawing tools. And also fill rectangle. What's the difference? The difference is one draws a coloured in rectangle and the other one isn't. You can figure out which one is which. What's the syntax? We'll have a look. And we're going to draw a checkers board. So draw a rectangle. You specify X and Y, which is the top left corner of our rectangle. And then it's not X2 and Y2, which would have perhaps made sense if you're talking about the bottom right-hand corner, I guess, but instead they said, no, we'll go for width and height. And remembering everything is upside down world here, positive head down and downward. So if I drew a rectangle that said 0, 0, 5, 5, it would start in the top left-hand corner and go across 5 and down 5. Let's do that. So I'm going to start a new document. I've got lots of them here. Draw. Let's call it board. So, menu, draw, shape, or rectangle. So if I went from 0, 0, and I made 5, 5, and in a moment you'll see a tiny little rectangle in the top. Well, it's actually a square. It's part of the family of rectangles, right? So we could make it bigger. Remembering our screen is quite big, I'll make it really big. Not overly exciting yet. Let's go back. So width and height, hopefully we've got the idea of how that works, and fill rectangle will do exactly the same, but make sure you set the color first, otherwise it's kind of boring. We'll make sure we set the color. So we're going to do a checkerboard, like what you saw on the screen before, and you can call that as a program in its own right. So if you want to redraw the checkerboard, it's actually quite handy to have a program called board and then just splash it on. So there's our checkerboard. And we'll say that every second square is a different color. It could be white, or you could just skip them and not draw them. That works as well if you want them white. And it would look prettier, I guess, if we have an outside border. We'll work with that in a minute. And what else do we need to do? We need to consider the size of the rectangles and where each square is laid. So the top row of black squares, I'm going to say start at 20, 80, 120, 160. So we can see we're probably going to create some sort of a loop to draw those 4 squares. And we're going to skip along and draw them. If I'm using those numbers for X, we'll make them 20 by 20, obviously. And the next one, bear with me, my PowerPoint's still catching up. So each square is going to be 20 by 20. And obviously we'll have to create some nested loops if we're going to draw the rest of them. So I'll have a loop to do the top ones, and then we'll need to progress down the screen. And you don't have to do them in black. All right, so let's go. We'll come back to our board. And for I equals, now you see, sometimes it does this, it jumps with all these new programming things that we've got in there. Sometimes you'll see the syntax, but it will work itself out. We said we're going to start at 20 and go up to 160 in steps of 20. And let's just try. I'm going to get rid of the draw rectangle because I want filled rectangles. Draw shapes, fill rectangle, and we'll start it at our X coordinate. And then the Y coordinate, they're all going to go along in the same row. Let's put it at 20. I think that'll be okay. And we'll make them 20 by 20. And 4. And what colour would you like the rectangles, Brian?
I reckon black would be good.
Black.
Yep.
Right.
Just go 255, 255. Oh no, 000. Yeah, because the other way.
Which one's which? Let's find out, shall we? Let's run that.
It's by light, isn't it? Yes.
Well, that's pretty silly. You know what I've done there? Let's go back and have a look. I need a step size of 40. Now let's try that. There we go. Looks like a chessboard, only not. So yes, the 000 means no colour, no colour, no colour, no red, no green, no blue. If you wanted them white, then 255, 255, 255, or whatever colour you want. So we talked about a nested loop to make it go down the page, perhaps. So we could try for, let's say, J equals 20, to, let's say, 160 again in steps of 40. And I wonder if that would be all we need to do.
Won't we?
Let's try it. I'm going. Ooh.
Okay.
Looking pretty good.
Because you've jumped every second line. But we want to have them diagonally, yep.
Yeah, we've got some more rectangles or rather squares that need to go in there. So another set of loops. So we can copy those. Control C. Now, where would we need to start those? I think we'd need to start on the next row, wouldn't we? So let's say 40. And do we think 180? Oops, that's not a very good 180. I was watching the wrong screen. And let's think 40 and 180. Let's see if that works. Thinking on the fly here. Oh.
Okay.
But you see about my little annotation at the start, we really need to have a border around it. Otherwise, it kind of doesn't hold the board in place. So once we've done that, we would probably want to draw a rectangle all the way around the outside. Draw shapes for rectangle. And I'm thinking it starts, now does it start at 2020? I think it does.
Yep.
And
181, or is it 200, 200?
I think 160, isn't it, the height and width? Because you're thinking X2, Y2, aren't you? We're going to find out in a minute. Let's try it. That's pretty good. That's good enough for our checkerboard. Now, we called that board. Now, let's go back to the top. Now, it's difficult to catch on the webinar, but I'm watching it on my computer. I can see it sort of go blob, 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 and draw them in. So here's the other tool you want to use and get used to using. I can do things like Control, and I'll say, I'd like to use the buffer. So you alert the program to say, use the buffer, and then all of the drawing will happen in the background, and when you're finished doing the drawing, whatever part you want to then display on the screen, you paint what is loaded in the buffer. So Control, Paint Buffer. As I said, for the webinar users, you won't notice much difference, but try it on your calculator and you will see it. So we'll run that, and it just goes, boop. There's no animation, it just paints it. It's done. And if we want animation to be fairly quick, those transitions where it just goes, it's there, that's what you do. So I can call that up from anywhere else. So from some other program, I can just say, right, draw the board. So if I created another program that said game, first thing I might do is call up the board. And that will call the board program from this and then just draw the board. And then I can add more stuff to the board, like a piece on the board or whatever else it might be, draw discs and so on. So if I go back to that pedaling one, you can see I use the buffer up here. I've got X location and Y location. That's the current coordinates of my cursor. And the other thing we'll probably want to see is how do I then check what key is being pressed. So while K is not equal to escape. Let's go back into here. I've got one I think I saved earlier. Let me just check. Yes, this one here. I'm just watching the time. I don't want to run over time. So here's a nice little program. It just checks the key. So key is assigned equal to blank. And while key is blank, go and get it. So it goes into that little loop, this one here, and it will go round and round inside that loop, waiting until someone presses a key. And then it's going to display the result. There are places we can get the results, but I think you'll see it's pretty obvious when I run it. So let's just run this program. And it's not doing anything. It's just waiting for me to press a key. So I'm going to press the right arrow. Oh, look what the key says. it says right. So I'll run the program again and see if anyone can guess what will happen if I press the left arrow. Pretty obvious. All right, we'll run the program again and I'll press the escape key. I don't think I need to go any further, do I? So then in my program here, I then decide what to do if the person presses the right arrow key. So in my pebbling program, back here, if they press the escape key, then it just increments something off to the right and draws another little rectangle. See if I can see that bit of code. Draw a rectangle at X location, Y location. So if they've pressed the right arrow key, it will change the X location. If they've pressed the up arrow key, it will change the Y location, and that's it. The other thing it does do, so that they can't wander off the screen, it checks to make sure, depending on their current X location, if they were to go one more step to the right, it just ignores it again. So let's just scroll down where it's doing here, so you can see it's doing some maths here to stop it wandering off the screen. There's a lot in that program, a bit more than what we've got time to cover in this webinar, but I think most people should be comfortable that at the very least they could draw a board like we had up here just by using the fill rectangles. Let's see, we'll add one more thing in here. Let's put a disk. Now, it'd be nice if you could try and just go back here and see the board, but you can't because the canvas is gone. So I want to draw a disk, let's say in the top left-hand square of the board. So let's go Menu, Draw. Actually, let's not do it in there. I'm going to save that one. Control B. And let's go into here. So let's just check to make sure that works. Just draws the board. But let's get it to draw a disk. So Menu, Draw, Shape. So a fill circle. I think we're probably confident that it's going to have an X location, a Y location, probably a diameter. So let's try it at, I'm trying to think where the centre of that piece might be. Let's say 30. Yeah, I'm thinking. And we're going to find out in a minute whether it's a radius or a diameter. Let's try 5. And we'll run it. Oh, I haven't set a colour yet. Let's set a colour. Now, you can change the colour anywhere, obviously, within your program. Let's make it a red disk. Red, green, blue. That's not too bad. Well done, Brian. Thank you. Let's draw a little red circle. Now, then, to get one more step into that program, we would then look for that key thing. Let's go back to this one. I'm just going to copy this bit. Copy. And we'll go into this one. Paste it. That worked. And you could write another program that just recorded the key event, right? So we could say if key equals right, what would we do? I think it's then, isn't it? Then there's space there. Then we might want to redraw the board and put the fill circle off to the right, wouldn't we? And that would then be whereabouts, Brian, since you did so well on the last one. I'm going to think 50.
50, yeah, because we're adding 20 across.
Yeah, but we don't change the Y value because we went to the right. All right? So end if. Otherwise, we're not going to do anything. All right? Let's see if that works. Now, it says running, and you can see I pressed the right arrow key, but it had already erased the board before I had a chance. But you can see it actually did put it off to the other side. And remembering our board program changed the colour of the board. So, yeah, I would need to then change the colour in here, set colour to red, like that, and to move it across. Now, if I moved in any other direction, we wouldn't see it. And that's basically it. I think we're almost out of time. Did we have any people with questions or wanted to see some of the other commands, perhaps?
Now's your chance to type them in.
If we haven't got any questions there, Brian, there is a set window command. You just quickly jump into that one. So I'll type in set. For those people that don't like the current window settings, you can see you can actually set the X min and X max, Y min and Y max. So you can set the dimensions of the window to whatever you like. But the default size is what we had up on the screen earlier.
200.
And you see.
Yep.
Yeah. And the set pen, which was another command I used in that pebbling one to make the current location that I was with my cursor, you can make the lines thicker. So set pen is not the colour, it's the thickness of the line that you're using to draw the shapes. So anywhere between 1, which is the thinnest, and 3 being the thickest. So if I'd gone back here, let's change our fill circle to menu, draw shapes, draw circle, and let's set pen 3. Oops, I think that's right. We'll find out. No, too few arguments. What did set pen want?
It was there set in the wizard. Yep. Your thickness.
It needs a thickness and a style.
Yep.
One is the thinnest, and where's the style? Smooth dotted dash. So we do need one extra thing, so comma 1. So it looks more like a donut on the board now. Sorry about that. We're going to the brain. But hopefully people have seen
it's from the circle. Yep.
Play around with it. It's still a circle, but it's got a very thick line as the drawing of the circle. So we've only got about 2 or 3 minutes left, Brian, so I'll hand back to you.
Okay, well, thanks for that, Peter. I think that's quite interesting. As I know students of mine, a lot of them, as far as when you talk about coding, a lot of them are interested in game design or pursuing some sort of career in that area. So I dare say that's why this is gaining traction in the coding of the Nspire, or the latest generation of Nspire.
And I only just saw your joke there before, Brian. Really sad. Do we have time?
Look, it was begging for it, Peter. Yeah, I thought you'd put it out there, and I thought I'd better respond.
Yeah. Never mind.
Well, I was so pleased that we did have time for the clock arithmetic. So once again, Peter, you've treated us very very well there with showing us some of those new features and clever ideas with your coding as you develop that step by step and show us how that's done. Now is the opportunity to ask any final questions of Peter, because he's now reading the chat while I run through these final slides. Or you might like to just type in a word of thanks to Peter, because I think he's done a pretty good job, as I knew he would. I will close the event shortly. You will be taken to the site for feedback, and then fairly soon you will be receiving an email with your certificate of attendance and links to the recording of the webinar. People often ask, is this being recorded? Yes, it is. There is an archive of past webinars, we call webinars on demand, on the website. You will have either registered for this webinar through the webpage, Texas Instruments Australia webpage, or possibly following a link from the newsletter. And you have just attended the final webinar for our program for this year. So thank you for joining us. And I hope to see you again in the new year. If you want to see next year's program, the newsletter is probably the best contact for that. So if you're not already subscribed to the newsletter, I would encourage you to do so. If you visit us at one of the conferences in the near future, we'll be at conferences in Perth and in Melbourne, and another event in Brisbane coming up. Just come and see us at the TI desk and enrol for the newsletter. The other way, of course, is many people have already discovered our new blog, which is t3australia.blog. I actually typed that address into the chat a little earlier, and all our upcoming events are notified in that. Remember, at any time, if you do have questions or queries about the TI technology, not just the calculators, but the software, the licensing, the STEM support materials we've got, there's the phone numbers to call. And that will bring us to a conclusion for tonight and for the 2019 webinar program. Thank you once again to Peter, and thank you all for attending. Good evening to all.